simple presentation, a simple series of images inspires me to remember a little bit what we have been talking about last time. First of all, your questions, ok? Domande, avevate delle cose da chiedermi, mi ha detto, il che è ottimo. Questions?
Mi avevate detto che alcune cose non erano state chiare, quindi bisognerà risolverle.
Nessuno osa parlare.
Sì, infatti, forse sono ancora un po' addormentati.
Facciamo dopo. Era sul concetto di cono di luce o? Sì. Ma cosa?
Io non faccio bene il diagramma spazio, di spazio praticamente, perché è tempo per C.
Sì. Allora, non si fa questa cosa. Lo faccio in italiano. Quindi un asse rappresenta X, un asse abbiamo chiamato C per T. Devi mettere attenzione, quello che conta è che questa grandezza qua, quando il tempo passa, il corpo descrive questa linea qua. Se il corpo non si sposta anche nello spazio, cioè per esempio, se io sto fermo qua, la mia linea è questa. È tutto lì. Non è importante poi dal punto di vista della costante 5 metti qua, perché comunque se t passa, se t aumenta anche ct. Abbiamo messo il ct perché l'idea era di cercare qualche combinazione di intervallo di spazio e intervallo di tempo in modo che sia assoluto, cioè non dipendesse dal sistema di riferimento. Però chiaramente non puoi fare questo in fisica, Con più o con meno, adesso se non sta al segno. Questo non ha nessun senso in fisica, perché questo sarebbe in secondi al quadrato, questo in metri quadri, veramente non puoi sommare. E quindi ha senso anche dal punto di vista dimensionale dell'unità di misura C alla seconda. Ok? Questo 1 e 2, comunque se non metti C alla seconda qua, anche, cioè hai il rischio che questa quantità poi non è invariante sotto l'azione della trasformazione di Lorentz ispirata. Le LF, questo è il motivo di fare. Ne approfitto per dire, so, a concept which I haven't maybe stressed enough is the concept of the world line. Your question remembers me that a world line, una linea d'universo di un corpo puntiforme. Immaginiamo che, let's imagine that we start with time t equals 0. Here we have a particle, simple elementary particle, point-like object, ideally a point-like object. And the world line is just a line that this particle describes in space-time. And it must lie within the light cone, the future light cone. So the world line can be like this, for instance, like this. La linea d'universo è semplicemente la traiettoria nello spazio-tempo. Sempre and always inside the light cone and not having an inclination more than 45 degrees. Otherwise you go faster than the speed of light. Remember? So I repeat, if you have an object, a point-like object, that stands still, which has no motion, which I was saying earlier on, which has no motion, it is always moving in space-time, not in space, like we did here and now, but it is always moving in space-time. That means that the world line is a straight line. Only time is passing when you move through, etc. So I hope I have answered your questions. Other questions? Well,
Forse c'era qualcosa su Pineni che potrebbe chiesto.
black holes. Buchi neri, black holes. So this is a summary. You remember the Maxwell field. This is another presentation I did a while ago somewhere else. I think, yeah. This is we have been talking about coordinate transformations. So in the fact that according to the relativity principle, the form of the laws should not depend on the inertial rapid frame. Then the various contradictions, and then the two fundamental postulates of the relativity principle, the constant speed of light in special relativity. Yes. The Lorentz-Meteorite transformations, which is and the relativity of length and time, blah blah blah. And then this important concept, a new absolute quantity in space-time interval, delta S, which delta is t squared, is a mistake, sorry. With a minus and a plus plus plus. That is the point. Maybe I should add some little thing here. Last time I had been just writing that delta S squared is something like minus c squared delta t squared plus delta x squared. Now this is the case, this is true, if you have just only one space dimension. But in reality we have at least 3 spatial dimensions. And so this would become, by analogy, first minus t squared plus t squared plus delta x squared. So what about y and z and so forth? Well, just add plus delta y squared delta z squared. So it's not very difficult. So this means that this is the effective Euclidean space separation between 2 points, events, and this is a time-like separation between 2 points. Right? 3 spatial dimensions, x, y, z, okay, and 1 time dimension. So in technical terms and in the books you will call that 4-dimensional Minkowski spacetime. But don't be afraid about the 4 dimensions. It's just time, which is 1 dimension, and space. So in technical terms also, this is called not a Riemannian structure, but a Lorentzian structure. Lorentzian manifold. You know the word manifold? It's a mathematical thing. It means varietà. La varietà è uno spazio che ha proprietà. Però descritte da questa cosa che ti dà la distanza effettiva, separazione effettiva tra 2 punti. Sì,
Vi ricordate quando l'anno scorso avevamo guardato quegli articoli sul 9 che avevamo parlato di varietà topologiche che contiamo in fila? Ecco, è stato forse l'unica volta in cui abbiamo vagamente accennato a quella roba lì, ok? È lo stesso concetto.
Adesso vedremo quando le lezioni successive. We will see that the the sphere S2, okay, simple S2, that is a manifold. It's a particular example of a manifold. Cylinder is a manifold. Plane is a manifold. I mean, flat surface. All examples of manifolds. Of course, if a mathematician would be here, he would tell you, oh, well, a manifold needs a differentiable structure, continuous, blah, blah, blah. You will see this, you will learn this later. This is just a technical term, mathematical term. But I mean, usually, the distance between 2 points, elementary separation between 2 points, on a manifold, or whatever sort of manifold, the geometrical manifold has a Riemannian structure. Riemann. So the Riemannian equivalent of that, Riemannian manifold, that would have all pluses. For instance, a 4-dimensional Riemannian manifold would have plus. Here, you don't have plus. You have 1 minus. This is Lorentzian, that's all. It's a definition. Minus, plus. Minus, plus, or plus. This would be Riemannian. Or Euclidean as well. Sometimes this is called Euclidean. But technically, I think mathematicians, pure mathematicians, difficult people, they prefer to say Riemannian. This series of signs is what we call, technically in relativity, the signature. Termine tecnico, il segno, non so se c'è un equivalente in italiano, the signature, che sembra la firma, no? È un po' la firma, sì. Le cose lorenziane hanno un meno da qualche parte, meno 1. E le cose riemanniane hanno tutti più. Okay, this is technical. Don't worry too much about it. Ah, yes, and I wanted to add to this picture. Can I erase this to your mind? Yeah? Oh, if you have a registration. What can I say? Ah, yes, this one. So, we have this sort of thing here. There is a differential notation for that. It is exactly the same. Don't be afraid. Okay? You have, instead of the delta, we have ds squared equals. It would be like this, minus c squared dx squared plus dy squared, dt squared, plus dx squared plus dy squared plus dz squared. What is dx for a physicist? It's just the spatial separation between 2 infinitely close neighboring points. È un differenziale notazionale. Mathematicians hate this, but we physicists use it all the time. So there's no fundamental difference between that notation and that notation. This is why you see dx and dt. Do you know, you have been studying derivatives, isn't it? First derivative, second derivative. Integrals, primitive?
Yes.
Yes.
Yes, very good. Well then, the primitive of a function always specify the variables with respect to which you are calculating primitive functions. This is or if you prefer, also calculate the derivative of a function, the total derivative of a function with respect to that variable. So forth. I will not go too much yet today into mathematical detail, but we will do a little bit of mathematics next time in order to explain this. This is also called, and I will get closer and closer to that, because it seems difficult, but in reality it's not very difficult. You just need a bit of, you need to get used to it. You need a bit of time and a bit of patience. And don't be afraid of big formulas. Just be calm, relax. Step by step you can always get it. This is called the metric. Metric. The metric gives you the structure. The metric gives you the way to calculate, ultimately, the total effective separation between two space-time points, or between 2 points in ordinary geometry. Metric means measure, means distances, right? This gives you the distance between 2 points in Minkowski spacetime. This distance here, only this part, you could call this dl squared. This is just Pythagoras in 3-dimensional Euclidean space in Cartesian coordinates. This is just the distance between 2 points in 3-dimensional space. A point here, a point there. How do you calculate the distance, the Euclidean distance in geometry? dl. Well, you do Pythagoras in the x direction, but also Pythagoras in the y direction, and Pythagoras in the z direction. I mean, it's just Pythagoras 1, 2, 3 times. Okay? So this is not very complicated, really. This is just the usual distance you have in geometry between 2 points. This is the distance of the effective space-time interval between 2 events. That's all, right? And this structure we will call the metric, but that's for later on. Essentially, this is the exercise, I found it somewhere in the book. The exercise which I asked you to do. Did you manage to show that the space-time interval is invariant? L'avete fatta?
Avete fatto?
Eccolo qua. Si dimostra che you show that x prime squared minus ct prime is equal to x squared minus ct. So the expression is the same if you do the Lorentz-Fitzgerald transformations with Tate gamma contraction vector. So it's not very difficult. If you want, you can get that. Yeah. Right, this is the extremely important concept indeed. You remember the light cone structure of space-time, I mean the causal structure of space-time. Remember you have for any point a set which is the set of all the points which could be influenced causally by things that happened there. And the past light cone is just the set of all the points in space-time which can eventually, if something happens, causally influence what happens here. Now these are future applications. This is a diagram of Minkowski space-time invented by Roger Penrose. The the very nice thing is that this light cone structure is still around. You can get the whole thing, even when there is a black hole. Yes, these things here is what it means for an observer to enter the light cone of another event and be aware of something. If they have two light cones overlapping or intersecting. This is the so-called causal diamond. It means that the past light cone intersects the future light cone of another point. So they can share causal effects. This is, I will explain this later on, the famous black hole, the Schwarzschild black hole solution. And you see that this event horizon here is a cone, is at 45 degrees, because the boundary of a black hole, i.e. the event horizon, is a light cone, is a particular type of light cone. Because if you get in there, in order to get out of the black hole, you need to have a speed greater than the speed of light. So you would be inclined more than 45 degrees to get out of it. But you can't. Once you get in, you hit this strange set of points, which is the singularity. This is a strange consequence of general relativity. Now, why is this all very, very important? Not only for that, but this is a problem which I would like to explain later on. It's one of the problems, or original problems, of the standard Big Bang theory cosmology. This is the theory where general relativity is very important. And you see here, the past light cone of space-time plays a very important role. I'm not going to explain it now, of course, but later on. Now, here we are with our lecture today. Right, the fact that we need general relativity. And remember, we are asking ourselves, why do we need general relativity? Well, the first thing is there's a special relativity, so GR, general relativity. The first thing is that special relativity is restricted to a particular class of reference systems, the inertial reference frames, only inertial reference frames. Remember that? And the question is, what are you going to do with all the problems which deal with accelerated things? In this context, how, for instance, how are you going to think about the problem of absolute motion? I mean, the non-existence of absolute motion. I mean, you know that when you are in an airplane, you are flying at normal height of 10 kilometers, you know that the airplane is going at 800, 900 kilometers per hour, right? You know that in virtue of the relativity principle, if all the windows are closed, if you don't hear any sound, okay? From within the plane, being in the plane, doing any sort of experiment, you cannot show that you are moving. Relativity principle. Otherwise, if you would show, if you would detect some observable effect, then the relativity principle would be contradicted, right? You can't. But now, if the plane is taking off, you have to imagine the plane accelerating linearly, hopefully, linearly, that means that you feel a dragging, you feel a push towards the back seat, right? On the seat. So what are you going to think? Even if the windows are closed, even if you don't hear anything, even if you don't receive any information from the rest of the world, you are going to think, oh, now we are moving. If you have a glass of water filled and the plane is accelerating, the water might spill out of your glass. So you see an effect and you think, now I can show in an absolute way that we are moving. So how are I going to deal with that? Now Albert Einstein is going to generalize, if you want, the relativity principle from the class of inertial reference frames to any reference frame virtually, I mean to the class of accelerated frames, linearly accelerated frames, but as we will see today, also rotationally accelerated. You know that rotational motion is an accelerated motion, don't you? And a rotating frame is not inertial. Right? By the way, are you sure that you know what an inertial frame is? Frame means sistema di riferimento. Are you sure that you know what an inertial reference frame is? Yeah? Yes? Yes, but why is it called inertial reference frame? E se questa classe, if this lecture hall here, this classroom would be rotating, right? We don't see anything outside, but we are just here, and around the central axis, this classroom would be rotating. What would happen? What would you observe? What would you feel? Questa classe comincia a girare con un asse centrale, sempre più velocemente.
Andiamo.
Yes, andiamo. We feel a dragging as well towards the outer part of the reference system. So this is not an inertial reference frame, because if initially you leave an object at rest, and if the net force, I mean the resultant force, is equal to 0, the object is moving anyway. So this is not inertial. This is a non-inertial state of motion. Yeah? So this is all to do with that first question. I will discuss this just in a minute. But the second point is, this was a big question for Einstein. Albert Einstein himself. Newton's theory of gravitation violates the postulates of special relativity and is inadequate for cosmology. So there's a big question here. Newton's theory. Newton's universal relativity has two problematic aspects, two problems. One is postulates or axioms, right, of special relativity. Why? I'll tell you. So this is point A. The second point is, how about cosmology with Newton? This is point B. If you're okay with that, if you don't mind, I'm going to explain first this problem, these two problems here. You will see that Newton's theory of universal gravitation, very important element, but there are problems if you think about that. Let me just get on. It's all sort of summarized here. Yes. well, this is obvious, I mean, we know all that, but I mean, sorry, have a question? Newton's theory, yeah. Oh yes, sorry. The law, yeah, la legge. Newton's law, Einstein's law, physical laws, it's in English. Special relativity and Newton. You remember that special relativity depends and has in it a fundamental speed, a limit speed, an upper limit, un limite superiore per le velocità, la velocità massima, a maximal velocity exists here, upper speed limit. And this speed limit is absolute as well. And it's the speed of light in vacuum. Yeah. So, Newton's law of gravitation says, on the other hand, this implies that gravity acts at a distance. I mean, we know that one given mass, one given object, attracts any other objects in the universe, right? But instantaneously, I mean, if you have another object in the universe, it immediately feels the gravitational field. It means that it acts at a distance, agisce a distanza. Gravity acts at a distance. At a distance. L'azione della gravità, the action of gravity seems to be instantaneous, so it seems to be infinitely fast. You understand? You have the Earth here. You have an object here, you have an object there. These objects instantaneously feel the gravitational field. No matter how far they are. Gravity will be very weak if you are very far, but no matter how far they are, they instantly feel this mysterious gravitation. That means that there is no speed limit for the gravitational interaction. This means that gravity is something instantaneous. This is very different from Maxwell's theory. I mean, electromagnetism has a speed, and it is the speed of light. So this is very, very different. If you, even Isaac Newton, back in the 17th century, found this thing puzzling. Do you know what two great books that Isaac Newton wrote? Isaac Newton's great and big publications. Which ones? Due grandi, grosse pubblicazioni di Isaac Newton. Yes?
No.
Ah, ok.
Voi devo fare la mano.
Sì. Vabbè, obvious. Newton. One is, so this is vale la pena, it's worthwhile. Think about it. It seems obvious, but it's not. First publication is, well, first, a big one, very important one, the most fundamental. It contains the foundations of all Newtonian mechanics. It's amazing, totally amazing. It's called Principia Mathematica Philosophiae Naturalis in Latin, because it is written in Latin. Principia matematica, filosofia, sorry, it's the English style, philosophiae naturalis. 1680 something, I don't remember exactly. In Latin, all mathematical demonstrations are geometrical in the Euclidean style. It's very, very hard to read. Except the first part. The first few pages are fascinating because they contain the very clear expression of the axioms and postulates which Isaac Newton explains. It means absolute time, absolute space. It's really worthwhile looking that up because it's totally amazing to see that a person thinks that, okay, 400 years ago, a person just states that time flows uniformly and absolutely in a way which is completely independent from the presence of other material objects around. And space is the same thing. Space exists in an absolute way, and it exists in a way which is independent from the presence of other material objects. Why am I saying this? Because now we are going towards Einstein's theory, and it's exactly the opposite. Time does depend on the presence of material objects, and the structure of space does depend on the presence of material objects. Amazing. Now, how are we going to get there? Wait. So this is one publication of Isaac Newton, and you know that Isaac Newton was a little bit strange guy. Huh? He was very afraid to publish his own findings. And it was thanks to the English astronomer Edmund Halley, from the comet of Halley, that finally Sir Isaac Newton published his book. And this contains the 3 principles of Newtonian dynamics, very clearly, and the law of universal gravitation. Yes? So this is amazing, isn't it? 4 principles, 4 laws, and they explain the whole mechanical universe. Chapeau. Now he has written another treatise. Which one? Optics. Written in Old English. Optics, optica. This is written in English and it's easier to read. It's fascinating. All the findings and thinking of Newton about the nature of light, la natura della luce. Here. Beautiful. Also, however, in this book, at the end of some chapters of this book, you have a long list of questions, which are called queries in English. Queries. All English word. Quasi, I think, in Italian. Queries. In one of these queries, Isaac Newton, thinks about gravitation and asks himself, how is it possible to be so fool to believe that gravitation can act at some distance through pure vacuum? And that if something is propagating from the Earth to the Moon and to other objects, with what speed, if it is propagating, with what speed is this thing propagating? There's no speed in Newton's theory. Newton's theory just tells you on which factors the gravitational force depends. In Newton's theory, you see that gravity depends on the masses, on the distance between objects, etc. So Newton himself was very perplexed by the nature of gravity. And if you read that, you see Newton's true thinking about gravitation. He was very surprised by all this. Now, part of the answer to these questions of Newton will be found by Albert Einstein. In another treatise, written in an article, published in 1915, and this will be called, in German, Die Grundlagen der allgemeinen Relativitätstheorie. Okay, the foundations of the general theory of relativity. So we start with Latin, English, and German. We will do relativity in English, right? Not in German. I can't do it in German. A little bit, unfortunately. Sorry? Fortunately. Yes. But you know how you say speed of light in German? You should know it. Somebody knows? Lichtgeschwindigkeit. Geschwindigkeit is just speed in German. It's a word like that. It means speed. Licht. Technical German is quite easy and it's not very difficult. Except a few strange words, of course. So you see, the first problem is, again, this amazing upper limit, this speed limit, which must also physically be associated to fundamental interactions. So also gravity should have that. The second problem is even worse. I mean, it's due to the fact that, right, take a reference system O, right, as we have been trying to explain last time. Write Newton's law in this system. Okay, I write Newton's law in that system. 1 minus 2 over r squared. Splendid. But now, write Newton's law with respect to a moving frame, i.e. another inertial frame, which we usually call, say, O prime. What's going to happen there? So you can have, I don't know, F primed is G, if you assume G to be an absolute constant as well, first of all. What's going to happen with R, for instance, if you move along the R direction? This is a simple way to do that. Well, if you switch from one frame to another frame, you're going to have R is a distance, a length. Length contraction. Length contraction. That means that, you know, R prime can be R times the square root of 1 minus B squared over C squared. Yes? Yeah. So this means, well, I mean, you can write that as R prime equals R times 1 over gamma. So gamma to the minus 1. Because by definition gamma is 1 over the square root. You have that, right? So here you have a gamma to the minus 2 R primed, for instance. It would become, right? Something. I'm simplifying it. And what about the mass? It changes as well. Do you know the relativistic formula for mass, which you should use in some circumstances? Ah, okay. You can also speculate that mass is relative. You can also show that from relativity. The mass, the inertial mass of an object is equal to the rest mass over the square root. It's always the square root. Mass is relative in Einstein's theory. This is related, this can be shown to be intimately connected with the very profound equivalence between mass and energy. I can explain this later when we do the corresponding ESP.
Sotto il livello di trazione nella formula F' uguale G R, sarebbe R o R'?
Beh, in realtà sarebbe R' alla seconda. E dopo si vede che non sono equivalenti. Ok? Well, here, what am I going to have? M prime 1 times M prime 2. Okay? But these two quantities, these two forces are not equivalent, they are not equal. Vuol dire che l'intensità della forza cambia. Okay? The intensity of the force would not, this one is not equal to that. Why? Because of this formula. Okay? So this means that this means this would be equal to G gamma squared M1 times M2, because this is M, the original M, okay, over the square root, which means gamma. Gamma times gamma, gamma squared, over R prime squared. And indeed you have gamma to the minus 2 R squared. Unfortunately, you see that even if you take into account the mass, these gammas, they don't cancel out. Okay, it becomes gamma, they become gamma to the 4. And this is the original factor. These two forces, these two laws, they cannot be equivalent. This is what I wanted to say. Okay? That means, essentially, that Newton's law for universal gravitation is not consistent with the equivalence principle, con il principio di equivalenza. Why? Because you would see a difference if this is true. Another way to say this, if you want this to be equal to this, you will change G from one frame to the other frame in order to cancel out these factors. But then the form of the laws, there's the effect that gravitation would not change. And here you would change the constant of gravity. Also find that or something? Also erase this. So the conclusion is compatible with the relativity principle. RP, relativity principle. Yes?
Scusi, avevo una domanda sul gamma.
Sì.
Se noi scoprissimo la velocità più grande della velocità della luce,
sì,
cosa succederebbe alla riflessione?
Sì, giusto. Allora, gamma è tutti i fattori relativistici che dipendono da questa roba qua. se V è maggiore di C,
Non sei quella davanti proprio.
No, di parlare.
if V is greater than C, ok? Se V è più grande di C, qui ha un numero maggiore di 1. Sì? 1 meno qualcosa di maggiore di 1 è negativo, minore di 0. Quindi avresti una radice quadrata minore, cioè avresti una radice quadrata immaginaria, imaginary numbers. Questo vuol dire che la massa, per esempio la massa relativa o quantità associate, sarebbe espressa con numeri I per qualcosa, numeri immaginari, perché la radice quadrata di una quantità negativa non è un numero reale, e la massa inerziale non sarebbe più reale, sarebbe più un numero reale, sarebbe misurabile con numeri immaginari. Ipotetiche particelle che viaggerebbero alla velocità superiore della luce sono chiamate tacchioni, parliamo forse un po' più avanti, ma sicuramente non sono ammessi nella descrizione, dove si utilizzano numeri reali, quantità reali per misurare masse, densità, tempi e lunghezze.
Ma a livello fisico si sa cosa succederebbe o...
Sì. Ma non sarebbero nemmeno osservabili, perché il problema è che già quando V è uguale a C, e se V è uguale a C, gamma è infinito. È l'espressione matematica del fatto che non puoi, come oggetto che ha una massa, arrivare alla velocità della luce, se no la tua massa inerziale sarebbe infinita e quindi non sarebbe neanche possibile muoverla, cioè, entrare in uno stato di movimento se l'inerzia tende all'infinito. Questo è il problema. La teoria delle stringhe, string theory, che è una proposta di fisica teorica, nelle sue prime espressioni aveva questo problema qua, perché se cambi i postulati di base delle particelle, le particelle non sono dei corpi puntiformi ma delle stringhe, i calcoli sono più complicati, ma presa così ci sono delle soluzioni dove hai delle particelle modi di vibrazione di questa stringa nello spazio-tempo che prevedono i tacchioni. I fisici a tutti i costi vogliono eliminare questa roba. In fatalità esiste una ricetta, una nuova teoria che è nata negli anni 80, 1980, che si chiama teoria delle superstring, super string theory. E il super, l'aggettivo, cioè la parola super, vuol dire supersimmetria, una simmetria fondamentale ipotetica. Ma se aggiungi la supersimmetria alla teoria delle stringhe, questi tacchioni, questi quanti che vanno a velocità superiore alla velocità della luce spariscono. Sembra che la teoria delle superstringhe sia coerente da quel punto di vista. Comunque non riesce ad accelerare un oggetto che ha un'inerzia non nulla all'inizio alla velocità della luce. La luce va alla velocità della luce, ma facci caso, non ha massa. Un fotone privo di massa veicola soltanto energia, quindi non la soltanto l'energia da un tutto all'altro. Ok.
Facciamo il 5 minuti.
Sì, sicuramente.
5 minuti di caldo, però 5 ok.
6 hours later.
Right, so we start. So there are problems with Newton and special relativity, right? No upper speed limit in gravitation, Newtonian gravitation. Problems with The relativity principle, essentially because Newton's law depends on distance and mass, and this is all relative, and then you have to change things. But the second thing is problems with Newton's theory in cosmology. Now, what do you think about the universe? Is the universe, universo, is the universe finite or infinite? Spatially. L'universo è infinito, l'universo è finito. Finite. Okay. So let's start with the finite universe. So problems. With cosmology. This is called cosmology, right? Essentially, the universe is finite, and we will see what the problem is in an infinite universe. If the universe is finite, then the universe is a big, huge distribution of galaxies. We will speak about cosmology, but next time, a bit in a little bit more precise way, but not immediately. But imagine that the universe is very, very great, is enormous. You know that the size of the universe is very, very impressive, very great. It's so great that even the speed of light seems very slow. Even light is like a snail at cosmic levels. Cioè la luce è una lumaca a livelli cosmici, talmente enorme. Si dovrebbe parlare a livelli della cosmologia della lentezza della luce, the slowness of light. It's incredibly slow. I'll explain this next time, because this is cosmology. But now, just imagine a huge, great universe. The problem then with Newtonian gravity Newtonian gravity implies then that this universe ultimately is unstable. Unstable universe. Instability can manifest itself in two ways in this situation. You have a finite universe, and every single galaxy is attracted gravitationally by every other galaxy. So the risk is that the universe collapses gravitationally, because gravitation is ultimately attractive. Right? You could then think, so the whole universe just crunches. Yeah? And then the other situation, also studied by Einstein at the beginning, is that the universe could just evaporate. I mean, if the mean or average kinetic energy, okay, of each galaxy is too great with respect to the attractive gravitational potential, and the galaxies, they can just fly off into space, and the whole universe can evaporate. So you have to take into account, and you might think then, well, what happens if the average kinetic energy is exactly equal to, okay, the total proportional, exactly proportional to the total Newtonian potential energy in the system, usually called V, isn't it? Newtonian potential energy. Do you know Newtonian potential? It's G and minus G and then over R to the 1. Something like that. But this is an unstable equilibrium. You can't be sure that it's like that. Because even if one galaxy has a little bit more kinetic energy than this equilibrium, just implies that the universe evaporates. Or if the total kinetic energy is just slightly less than the total potential gravitational energy of the system, that means gravity is too strong and the whole thing collapses. If the universe is a little bit too hot, you can think of this as a gas of galaxies. If the average kinetic energy is a little bit greater, you have evaporation. If the average kinetic energy is just a little bit less than the total potential gravitational energy, the whole universe sooner or later collapses. So this is an unstable equilibrium. It's like, do you know an example of an unstable equilibrium? If you take a pen or pencil on a table and you try to put the pen on your table with a point, it never stays in equilibrium. Sooner or later it falls. Why? Because the slightest deviation from the equilibrium position causes a huge change. So this is a risk here. So this means you can't explain the existence of an old universe, because the universe, the Earth is old, the Sun is old, the solar system is quite old. You know how old the Earth is in the solar system? If you ask the Sun, how old are you? 5 billion years, 5 miliardi adesso ne avrà ancora il Sole per altri 5 miliardi di anni da brillare molto ma 5 miliardi e l'universo ha unità maggiori, 5 miliardi di anni. È difficile spiegare un universo finito, anche enorme, ma stabile. L'instabilità. E allora uno dice, allora l'universo è infinito. E infatti non avete difficoltà. Don't you have philosophical problems with imagining just an enormous empty space and just one island of galaxies in there? Maybe yes, maybe no. Immanuel Kant thought that the universe was a finite island of stars. And indeed, if it was only for our own galaxies, for our own galaxy, I'll speak about this much better later, but our galaxy in time, billions of years, ultimately will finish in a black hole, a supergiant, supermassive black hole, which is now already in the nucleus of our galaxy. Slowly, but surely. Right, it's a little bit more complex than that, but I mean, that is the point. The universe, the more you look at fundamental physics, the universe looks like a pencil on the point, not on the other side. Everything seems to be extremely fine-tuned and unstable and not stable. That's one of the biggest problems of modern cosmology. Well, imagine the universe then is not finite but infinite. Then the problem is that if you want to calculate the gravitational force that acts on one point in an infinite universe that contains a homogeneous distribution of galaxies in all directions of matter, homogeneous means uniform. Uniform means constant density. Then the net total gravitational force acting on one point somewhere is ambiguous, cannot be calculated mathematically, because you have the problem of infinity. How? This is very easy to see. Yes, one cannot define unambiguously, the gravitational field at a point in a spatially infinite homogeneous universe. So how are we going to show this mathematically? Well, you have to imagine an arbitrary mass, a point with a mass, in this infinite universe. Yeah? And you have to imagine that this mass is surrounded by shells of matter. Shells. Spherical shells. Then what are we going to do? What can you do? You can calculate the total gravitational effect on that mass due to one spherical shell, small shell, and then sum the total effect over all the shells and see what the result should be. So mathematically it's like this. This seems a bit complicated, there's an error there, but I think don't worry. So you have a mass in an infinite universe. The problem conceptually is that this mass will be attracted by an infinity of galaxies. Of course you might think, yes, but the gravitational interaction decreases with distance. It's 1 over r squared, isn't it? Yeah? So maybe everything is going to be alright. The danger with an infinity of galaxies would be that the total effect on m would be infinite. But if you have an infinite force or infinities in mathematics, it's difficult to calculate. It becomes ambiguous to define simply mathematically the gravitational field in a point. So this is true then for all the points in an infinite universe. So how do we do this? Well, suppose you have a spherical shell. Well, imagine, that there are galaxies all over here, right? Billions and billions of galaxies. You can select one shell of mass around here. This one. Okay? And now we want to calculate the gravitational attraction on and by this shell. Yes? Now imagine the distance, the radius is r, as usual. Right. Imagine the width of this small shell to be dr, o delta r, like you want. dr, lo spessore dello strato di cipolla. What is the total mass in the shell? M for a shell of radius r. You know that the density rho, mass over volume, is constant. It is the same number all over the shell, right? Because we are in a homogeneous universe. And it will be the same in all the shells, the infinity of other shells here, around the mass m in an infinite universe. Now, R then is the density times the volume, called the volume dV of one shell, of a spherical shell. What is the volume of this shell? Well, the elementary volume dV is the surface of the inner part, the surface area, e l'area, cioè la base per l'altezza è sempre un volume, no? The base area multiplied by height. base area is A, the area of the inner sphere, multiplied by dr. Altezza per area.
State capendo che conto sta facendo? Sta cercando di calcolare il volume del delta V, cioè dello spessore di cipolla, lo chiamano, capite?
Del guscio sferico.
Esatto. Cioè una sfera e c'è una sfera subito dopo, e la distanza tra le due sfere la chiama dr, ok?
È l'altezza.
Che è l'altezza, esatto, vuole calcolare il volume dell'intercapedine, dello spazio tra le due sfere, non so come chiamarlo, ok?
Il volume del guscio è base per altezza. Pensate al parallelepipedo, base per altezza e il suo volume. Pensate al cilindro, il cylinder, base P è 4 per l'altezza e il suo volume. Tipicamente qui hai la base della sfera, la sua area, chiamiamola A, this is A, multiplied by l'altezza. Qual è l'area di una sfera? The area of a sphere. Yes, 4 pi r squared times dr. Yes? Area times height. This is the volume. So I have the volume and so I have the mass. Yeah? The mass can be expressed. The mass where? The mass of this spherical shell. La massa di questo guscio. E la sua densità per il volume, perché densità è sempre massa fratto volume. Dunque massa è densità per volume, multiplied by volume. And so this becomes rho per 4 y r squared times dr. Ecco la massa. And now the problem is, ditemi se posso cancellare. Cancello solo quello. Calcoliamo la forza. Let's calculate the force F at R. Forza di gravità dovuta a una massa mr che agisce su m, non è il modulo, quella direzionale. Right, and so F of R is, as usual, Newton's law, G times prodotto delle masse, so F of R times m over R squared. This is the definition. Now we calculate that. Devi sostituire, we'll substitute instead of mr, which is this one, we will substitute that one into this one and see what happens. So what happens is, I will rewrite this smaller way. R is G and R times M over R squared times M of R, eccolo qua. Here it is. Rho times 4 pi R squared times the R over R squared. The problem is that R squared simplifies. Ciao, arrivederci. And this means that the contributo, cioè the contribution due to one shell is equal to F of R is just G times rho, okay, times 4 pi dr. So this factor is a constant, yes please.
Il secondante della forma.
Sì, esatto. Grazie. This is a constant factor. Disaster, the disaster for Newton is that this contribution, G is a constant, rho is constant because we are in a uniform universe, so it's always the same, should be, or I. M is your central mass, so that's constant. And now the problem is, if you sum over all the shells, you have to do this one, this is R, then this is an F, R prime, and etc. You have to sum over all shells, this. But there are an infinity of shells. Ci sono un'infinità di shells. Perché la cipolla è infinita. E allora lo spessore è sempre quello, equal width. La sommatoria di un'infinità di numeri costanti, cosa dà? Infinito. So F total tende a essere infinito. Actually, you could say, well, this is spherical, so I'm attracted this way, but also this way, and also this way, in equal ways. So this can actually cancel each other, because the contributions are exactly opposite. You have spherical, but it's still ambiguous, because you have to show that infinity minus infinity still a different problem.
Adesso, giusto per capire se ho capito, ma questo succederebbe in un tempo infinito, giusto?
Yes, sì, succederebbe istantaneamente, perché nella teoria di Newton la gravità non ha velocità, esiste subito. Questa strana azione che sta. Però sì, sei, ecco, vedi il problema. Proprio quello. Forse la soluzione alla quale arriverà anche Einstein è che c'è questa velocità limite anche per la gravità. Infatti l'interazione non da gravitazionale, no? Per Einstein sarà la velocità della luce incredibile. Ma già a quel tempo lì someone could say, okay, you could solve this and say, well, maybe the universe is not homogeneous. Maybe the calculation is a bit more complicated. This was around 1915, well, yes, very close, 19 or 10 something. And this is a strange but interesting universe model. It's called the model of Charlier. It's called Charlier's hierarchical infinite fractal universe. È un modello di universo non omogeneo, ma un po' frattale, nel senso che, in the following sense, one part of the universe, like this part, contains groups of galaxies, and it's equal to the next part, and it's equal to the next part, and it's equal to the next part, until infinity. So it repeats itself ad infinitum. Okay? Per una parte assomiglia a tutto e così via fino all'infinito. And the nice thing about this is that F total per una galassia da qualche parte di questo universo infinito, for a galaxy in this infinite universe, F total is finite. Un valore finito. Non c'è più l'infinito, non c'è più l'ambiguità matematica. Of course, naturalmente, our universe is not fractal. Our universe, as I will explain better in the next lectures, our universe seems to be homogeneous on large scales. But here the fundamental ingredient is that on very large scales you are very inhomogeneous because it's fractal up to infinity. Il nostro universo assomiglia a un brodo, una specie di rodaia uniforme, cioè di struttura uniforme, un minestrone uniforme, su scala però dell'ordine di centinaia di megaparsec. Okay? Ovviamente da vicino l'universo non è omogeneo, okay? Cioè io sono diverso da te, le cose sono molto disomogenee localmente su piccola scala, ma se guardi l'universo su scala 100 milioni di parsec, un parsec sono 3,26 anni di luce, dove sono 300 milioni di anni di luce. Su quella scala lì è bene o male è uniforme, non è frattale, assolutamente non è frattale. Quindi è un fatto astrofisico molto interessante e molto particolare del nostro universo, tornerò su questo, molto molto importante. L'omogeneità a grande scala, il principio copernicano, il principio cosmologico. Non occupiamo una posizione privilegiata, cioè qua è grossolanamente uguale a là, se là è una distanza di 300 milioni di anni di luce. Il diametro dell'universo osservabile sono 14, cioè sono circa una ventina di miliardi di anni di luce, un paio di ordini di grandezza, 1000 volte in più. Un anno di luce è la distanza che fa la luce nel vuoto in un anno di tempo. Sono circa 10.000 miliardi di chilometri, un anno di luce, one light year in English, in Italian, is roughly 10,000 billions kilometers. Come vi dicevo, questo è niente a livello cosmologico, ok? Very, very small. Proxima Centauri, the star. The solar system, you know how big the solar system is in terms of light? So if you have the sun here, and you have Pluto there, Pluto. The light would take about 6 hours to travel from here to Pluto, roughly. Okay? It's about 12 hours to the, maybe a bit more, 15 hours to the Kuiper belt, l'anello di Kuiper, da dove vengono le comete, cioè il materiale sporco primordiale, in cui siamo nati. Ok, the slowness of light, la lentezza costante della luce, è già visibile solo a livello del sistema solare, no? Se hai qua dei colleghi in missione su Pluto, dei amici, vuoi sapere come sta andando là, mandi l'SMS che 6 ore di andato un segnale elettromagnetico, se ti rispondono subito in 6 ore, 12 ore di pazienza, sapete un po' meglio. Ma peggio ancora è Proxima Centauri. Proxima Centauri is the star which is the closest to us. Okay? Alpha Centauri, Proxima Centauri, is at a distance of 4.3 light years. This is like if you are in a town, a little town, a village. Proxima Centauri is your neighbor next door. Just there. And if you want to speak with your neighbor, if you have friends or colleagues or family at Proxima Centauri, you have to send a message. It will travel 4.3 years if they reply, they will send another message, so you have to wait almost 9 years just to speak with your neighbor. La lentezza della luce, okay? Ma è molto importante avere la conoscenza. Poi you have Vega in the Lyra constellation. Vega is the brightest star of the Lyra. Vega is at a distance of 26.3 light years. 26.3 anni luce. Immagina comunicare con questi vegani. Sirius, più vicino è Sirius, la stella dell'Egitto, no? Sirius per nella civiltà antica egizia, quando il Nilo aveva ebb and flows, cioè quando aveva stagioni di acqua alta e bassa, si seguiva la stella Sirio. Questa si trova a 8,63 light years. Ok? Ci siamo ancora. La stella Polaris, la Polar Star, è stella Polaris, ha circa, non ricordo circa le date, sono 300 anni luce, 300 years. Ma cominciamo veramente a dover essere molto pazienti, 3 secoli all'andata e altri 3 secoli sono la risposta eventuale, 6 secoli. E questo è soltanto il piccolo villaggio, siamo sempre nel paese, eccetera, eccetera, eccetera. Ok? Perché quando si parla di universi, di omogeneità, l'universo è omogeneo su 100 milioni di anni di luce, non so se cominciate a sentire cos'è. La galassia, the galaxy, is an enormous super solar system but made of stars which are kept together with gravitation. It's always gravity. So if you have a galaxy, like our galaxy is a spiral galaxy, right? Spirals, has more or less the shape. In our galaxy, there are roughly 100 billion stars. 100 miliardi di stelle di sole. Il nostro è all the stars, they orbit around the nucleus of the galaxy, okay? And the size of our galaxy is about 100,000 light years. Il diametro della nostra piccola galassia, mezzo a miliardi di altre galassie, e 100.000 anni luce. Quella luce ci impiega per attraversarla 100.000 anni. La tipica distanza tra due galassie nel gruppo di galassie locali è 20 milioni di anni luce. Questa è la tipica distanza tra due galassie. Cioè, quando dici a una galassia dov'è il tuo vicino o la tua vicina, a 10-15 milioni di anni luce. E poi così. Su scale, on scale, su scale più grandi di 100 milioni di 300 milioni di anni luce, 100 milioni di parsec, l'universo appare omogeneo e non frattale, perché non è questa soluzione. Ok, parentesi già un po' cosmologica, perché ne avremo bisogno. Vorrei farlo di cosmologia relativistica. E allora, Albert Einstein, devo trovare una teoria della gravitazione coerente con tutti. Quindi si capisce
viene
genere, si capisce, cioè l'ammirazione per un fisico come Albert Einstein è giustificata, perché deve trovare una teoria della gravità che risolve i problemi cosmologici, ma che risolve anche il problema dell'inconsistenza, dell'incoerenza di Newton con i postulati della realtà speciale. Dunque deve emergere una nuova teoria della realtà, che non si limita alla classe particolare dei sistemi inerziali, cioè modi uniformi di intercettazione, no, tutti, che secondo Einstein le leggi fisiche fondamentali devono avere la stessa forma per tutti i sistemi fisici. Come fare? Allora, la chiave è stata anche questa. Uno dei postulati di base ci porterà al principio di equivalenza che inizio adesso, ma approfondirò mercoledì. The equivalence principle. There is a weak equivalence principle and there is a strong equivalence principle, but let's do one thing at a time. E Einstein essenzialmente dice questo, cioè i soldoni. The fundamental thing is this. To generalize the relativity principle from inertial frames to non-inertial frames or accelerated frames. Let's say accelerated frames now. A crucial concept is gravity. Crucial concept, central concept if you like, corresponds exactly to gravitation. So gravity is the bridge. Why? Just think about this example, this very simple example that I mentioned, the plane taking off. The plane, i.e. accelerating, and you inside the plane. You feel a backward dragging on your seat. You think, I'm moving now, I know that we are wrong, says Einstein. The plane could be standing still somewhere in space, and behind the plane, you could have a mass distribution that creates gravity that drags you onto your seat. And you can't distinguish between state at rest and accelerated motion. Essentially, the physics in a system in a gravitational field would be not distinguishable from physics in a system which is accelerated with the equivalent acceleration. So the very rough idea, before getting into some details of mathematical relation, is that imagine an accelerated system. I will do another drawing here, which is slightly more, this one. Imagine a reference system, a closed laboratory, L. Somewhere. And then you imagine, of course, a physicist in there or a normal person. Okay? Holding in his hand massive objects, and I'll tell you more about this, of course, I know inertial mass, gravitational mass, blah, blah, blah. But this is just to get towards the general idea, which I will explore much more Wednesday. Now, you have to imagine, for instance, this person simply standing there and dropping the mass okay, at rest. So he leaves the mass free to move. But of course, by inertia, this mass is not moving. It stays there. If you don't give it a kick, it stays there. So now imagine that also someone outside, but he doesn't know that, someone outside is accelerating the lift upwards in this direction with a constant acceleration, A. What happens from the perspective of who is inside the lift? Well, you see, while the lift is accelerating upwards, we have to take dimensions and blah blah blah. Equal person standing there still. Now he has been dropping the mass, but this mass, by inertia, is not moving up or down. It's staying there in space, right? But now, if the mass is still staying there where it was, also at this distance, this distance is not changing as well. What does this person sees effectively? He sees the object falling down. Because it is the bottom of the lift, if you want, which is accelerating upwards towards the ball, towards the mass. Right? So what, is this clear? What he sees is exactly what happens there. I mean, what is represented in this picture. What he sees is his object falling, accelerating towards the floor from his perspective. From our perspective, the ball is staying there and the lift is accelerating towards the ball. But Einstein then says, we have to finish. This is exactly the starting point. What happens in here is exactly equivalence principle with what would happen in a system which is not accelerating but standing still in a gravitational field. The ball would accelerate downwards as well, if the acceleration is exactly equal to the local gravitational field. Of course. So if this acceleration would have the value 9.81 meters per second squared, then what happens here could be reproduced in space where a laboratory during some time accelerates upwards with this acceleration. So there is a profound equivalence between acceleration and gravity, and we will see next time a profound equivalence between inertial dragging and inertial effects and gravitation. This is very, very important. Yes? See you Wednesday.